Hello, and welcome to this Talk Shock on designing AI applications. My name is Eric Green, and I'm a solutions architect based in Sydney, Australia. I specialize in helping public sector customers realize the benefits of using AI and machine learning services on AWS. AI and machine learning is helping organizations improve outcomes with better automation, predictive insights, natural language interactions, and data-driven decision making. It also enables organizations to transform customer experience, improve business operations with predictive insights, make better decisions faster based on machine learning predictions, and create innovation and innovative services and products. The AWS Well-Architected Framework helps cloud architects build secure, high-performing, resilient, and efficient infrastructure for their applications and workloads. Applying the machine learning lens of the Well-Architected Framework provides a consistent approach for customers and partners to evaluate AI and machine learning architecture. It also helps them implement designs that can scale over time. In this Chalk Talk, we're going to walk through designing machine learning applications guided by the Well-Architected Framework's 5 pillars: operational excellence, security, reliability, performance efficiency, and cost optimization. The operational excellence pillar concerns itself with running, monitoring, and gaining insights into systems to deliver business value and continually improve supporting processes and procedures. Now, the development of AI applications with machine learning can be broken into 5 general phases of discovery, building, testing, deployment, and operation. Within discovery, data is explored, you need to experiment with algorithms, and you need to define the key data features. During building, we create data pipelines, we train and optimize machine learning models, and we also evaluate the model performance and create scripts for retraining, monitoring, and other types of deployment activities. During the test phase, we make sure the end-to-end system of data pipelines, training, deployment, and monitoring all work together. After testing, we deploy the data pipelines, model endpoints, and monitoring scripts. And then we operate the system, monitoring the data pipelines and the inference endpoints for problems, while also monitoring the performance of the models as the data may change over time. Now, this end-to-end process is not linear. At any point during build, test, deployment, or operation, we may need to go back to previous steps. For example, if during operation the pattern of data changes dramatically, we may need to do additional data discovery and determine additional features to improve our model performance. Now, to ensure the ML workloads have a path to production, include cross-functional and domain expertise on project teams. Include all stakeholders required to develop, deploy, and support your ML workload. This includes business sponsors who help determine the scope and performance requirements of the ML models, systems architects determine how to integrate the ML capabilities into existing systems, a data scientist who develops and evaluates the machine learning models, data engineers that create and maintain data pipes, and ML operations engineers that develop the ML logic into production code. Now, early in the ML development lifecycle, you need to identify the end-to-end architecture and operational model for training and hosting. This allows for early identification of architectural and operational considerations that will be required for development, deployment, management, and integration of the ML workloads. ML projects are built upon layers of technical capabilities. This includes storage for data, models, and monitoring logs, analytics services that enable querying data and developing data features and pipelines, machine learning services for training and inference, build and deployment services to automate the end-to-end process, API frameworks to enable integration with applications, and management and governance services to secure, monitor, and audit the overall system. Now, data science discovery and exploration tasks provide background and insight into the creation and evolution of machine learning models. Document these activities in code packages that are managed and versioned in source control. Now, within a discovery environment developed on AWS, a common design would have SageMaker notebooks integrate with source control systems and leverage Athena and Glue query to query data and features from data stored in S3. You need to version inputs used to create models, including training data, training source code, in addition to model artifacts. Also version the algorithms used, featuring source code, hosting configurations, inference code, and data, and post-processing source code. AWS Code Commit in combination with S3 can be used to store and version all of these artifacts. A deployed model's performance and effectiveness may change over time. Identify metrics that indicate when a model version's performance and effectiveness is meeting business objectives, and create alerts at thresholds that indicate that a model needs to be retrained to trigger these activities. Alerts can trigger activities such as invalidating the current model, reverting to an older model version, retraining a new model based on new ground truth data, or data science teams refining your model retraining strategy. Now, SageMaker processing and training features allow you to develop an end-to-end ML pipeline that can be triggered using AWS Code Build when model performance thresholds are triggered. Minimize human touch points in ML deployment to ensure that ML models are consistently and repeatedly deployed using a pipeline that defines how models move from development to production. Identify and implement a deployment strategy that satisfies the requirements of your use case and business problem. If required, include human quality gates in your pipeline to have humans evaluate if a model is ready to deploy to a target environment. Now, the SageMaker endpoint deployment should leverage services like CloudFormation to deploy ML infrastructure consistently, and Code Deploy and Code Pipeline to automate the train, test, and deploy process. Identify and regularly collect key metrics related to the training, hosting, and predictions made against the model. Now, this ensures that you are able to continuously monitor the health of a deployed model across key evaluation criteria, such as system metrics, model latency, or detecting data drift. SageMaker Model Monitor allows you to implement machine learning model monitoring against established baselines, and CloudWatch enables its integration with existing applications, monitoring and automated operations process. The security pillar is concerned with protecting information, systems, and assets while delivering business value through risk assessment and mitigation strategies. Now, within a complex machine learning system where we have build and deploy, data processing, sensitive data, and ML training and inference systems all needing to operate together, a well-defined security architecture is critical to long-term success. The access level to machine learning systems should be taken into account when designing the system. Access to both the machine learning models and data sets used to train the model should be restricted to avoid data and model contamination. Inference endpoints should be secured such that only authorized parties can make inferences against the machine learning model. Now, all of the services involved in AWS Machine Learning System will leverage the identity and access management services to define the user's roles and permissions for interacting components. Data used for machine learning could be collected from multiple sources and needs to be available to various teams across your organization. Because production data is required for not only data science development activities, but also for training models, ensuring teams have end-to-end access to high-quality data sets requires a data governance strategy that ensures the integrity, security, and availability of data sets. Now, implementing data lake solutions with governance and access controls ensures developers and data scientists have controlled access to quality data for use in exploration activities, as well as training models. Data must also be guarded against exfiltration or mutation, Control what actions different teams in your organizations can take on the data and where they can send it. Services like Lake Formation allow a finer grained control over data access and also help in tracking the different data transformation steps. SageMaker also tracks all artifacts in the training and deployment process. As data from various sources is used in different phases of the ML process, monitor and track your data's origins and transformations over time. Data lineage enables visibility and simplifies the process of tracing data processing and machine learning errors back to the root cause. Strictly control who can access the data and what they can do with it. Preventative controls, auditing, and monitoring are needed to demonstrate how data has been controlled during its lifetime. CloudTrail can record all interactions between the various components in the machine learning systems, allowing them to be audited, as well as enabling real-time monitoring of suspicious activities. Regulatory concerns around machine learning systems include privacy considerations, such as those described in HIPAA or GDPR, where the machine learning system must adhere to the regulatory guidelines established in those frameworks. Unlike traditional models where the algorithms remain static, models leveraging machine learning and AI algorithms can evolve over time, so continued vigilance is necessary to ensure compliance with regulatory bodies. Now, SageMaker private endpoints ensure that all internet traffic between SageMaker and your application are within your virtual private cloud and don't cross the public internet. This is one way to improve the overall security profile of your ML application and also help meet these regulatory requirements. The reliability pillar is concerned with recovery from infrastructure or service disruptions, dynamically acquiring computing resources to meet demand, and mitigating disruptions such as misconfigurations or transient network issues. Machine learning workloads have additional requirements to manage changes to the data that are used to train a model to be able to recreate the exact version of a model in the event of failure or human error. Now, managing version changes through automation provides for a reliable and consistent recovery method. Managing changes to model inputs through automation requires versioning the various components involved in the machine learning process. Processing, training, and test scripts should be versioned by developers, and the promotion and deployment process should be automated. By utilizing code commit to version all artifacts, code build to package them, and code pipeline to coordinate the promotion from development to test and then to production, you can create a repeatable machine learning process that improves reliability. When deploying the same version of a machine learning model across multiple accounts or environments, the same practice of build once that is applied to application code should be applied for model training. A specific version of a model should only be trained once, and the output model artifacts should be utilized to deploy across multiple environments. This avoids bringing in unexpected changes to the model across environments. Let's walk through the process of training, evaluating, and deploying a model to see what this looks like. Now, the first step is to create features from your data for training and testing the model. Now, the model artifacts created by training jobs should be centralized in S3. Keeping multiple versions of trained models allows you to easily revert to previous versions when currently deployed models have issues. In order to test newly trained models, test scripts will deploy the new models as endpoints in the test environment. Test data is then used to create predictions that can compare to actuals. These evaluation results can then be manually reviewed by data scientists. Now, after reviewing evaluation results, the data scientist promotes the model to production alongside the previous endpoint. Code pipeline allows for this human checkpointed promotion process. Once a model is deployed, it is a best practice to have a blue-green or canary deployment strategy. With this deployment strategy, the newly deployed blue model endpoint will only handle a small percentage of traffic, and its performance is monitored to ensure that it performs better than the previous deployed model. Now, after a fixed period of monitoring, the blue endpoint is then promoted in production to handle the full volume of inferences, and the previous endpoint can be removed from production. SageMaker features such as endpoint versioning, production variants, and model monitoring make this process possible and help create a reliable machine learning application. The performance efficiency pillar focuses on the efficient use of computing resources to meet requirements and how to maintain that efficiency as demand changes and technologies evolve. Optimize compute for your machine learning workload. Selecting the best instance type for training depends on the algorithm used. Some algorithms, like XGBoost, may require large amounts of memory, so a large memory M5 instance may be best. Deep learning algorithms may require GPU acceleration, so using a P3 instance with GPU may be required. SageMaker training jobs have a wide variety of instance types available, so you can right-size training instances to the machine learning algorithm that you're using. In addition, by leveraging spot training, you can leverage high-performance instances for a fraction of the cost of on-demand instance types. The memory and compute requirements for machine learning inference is usually different from that required for training. During inference, models may have more needs for compute, memory, or GPU acceleration. And this is different from the requirements of the training the model. So for example, our deployed model's efficiency may be bound by CPU, so we would use a compute-optimized C5 instance for our deployed endpoint. This would better match the workload to the actual instance that it's deployed on. For algorithms that can take advantage of the parallel calculations provided by GPUs, you can also attach GPU acceleration to endpoints with elastic inference. For intermittent inferences that don't require real-time responses, SageMaker batch transforms are the most efficient way to run ML inference workloads. By using SageMaker Neo, machine learning models can be compiled to run more efficiently on target cloud instances. Define latency and network bandwidth performance requirements for your models. Some of your machine learning applications might require near instantaneous inference results to satisfy your business requirements. Now, offering lowest latency possible may require the removal of costly round trips to the nearest API endpoints. This reduction in latency can be achieved by running the inferences directly on the device itself. This is known as machine learning at the edge. Common use cases include transportation, robotics, devices, and factory automation. A good example for the need of edge inference is predictive maintenance. Near real-time inference at the edge allows for early indication of failure, potentially mitigating costly repairs of machinery before failure actually happens. Now, SageMaker Neo-compiled models can be seamlessly deployed to a fleet of IoT devices using Amazon Greengrass, enabling inference at the edge. Continuously monitor and measure system performance. The practice of identifying and regularly collecting key metrics related to the building, training, hosting, and running of predictions against a model ensures that you are able to continuously monitor the holistic success across key evaluation criteria. Now, to validate system-level resources used to support phases of ML workloads, it's really important to continuously collect and monitor system-level resources such as compute, memory, and network. Requirements for ML workloads change in different phases as training jobs are more memory intensive, while inference jobs are more compute intensive. All training and inference workloads within SageMaker generate logs that are sent to CloudWatch. And using CloudWatch metrics and Lambda through automated monitoring systems, you can create ML applications that are continuously monitored. The cost optimization pillar involves practices that enable building and operating cost-aware systems that achieve business outcomes, minimize costs, and maximize return on investment. From the initial design of your very first proof of concept to the ongoing operation of production workloads, adopting these practices will enable you to build and operate cost-aware systems that achieve business outcomes and minimize costs. Now, this allows your business to maximize its return on investment, and customers often want to begin with a cost discussion. But as we shall see, cost optimization really depends mostly on implementing a well-architected system according to the other 4 pillars we've already covered. So let's summarize how the previous points we covered impact on cost. Use managed services to reduce cost of ownership. Adopt the appropriate managed services for each phase of the machine learning workload to take advantage of the pay-for-what-you-use model. For example, model tuning is typically a compute and time-intensive process. So to avoid unnecessary charges, use a managed services that creates a distributed training cluster, executes training jobs to tune the model, persists the resulting models, and decommissions the cluster automatically when training is complete. Now, all the services we covered are managed services that will take care of the heavy lifting when implementing your machine learning system. SageMaker is a managed service that enables end-to-end machine learning, but the other managed services for analytics, build and deployment, management and governance, and storage all contribute to maximizing return on investment and lowering costs. Experiment with small data sets. While machine learning workloads benefit from large, high-quality training data sets, start with smaller data sets on a small compute instance to iterate quickly at low costs. After the experimentation period, scale up to train with a full data set available on a distributed compute cluster. When training with a full data set, opt for streaming data into the cluster instead of storing data on the cluster nodes. Create small sample data sets in S3 for exploration. Also, SageMaker allows to run training jobs in local mode within your notebook for rapid development before scaling out to large-scale training jobs. Right-size the training and model hosting instances. For model training and hosting, experiment to determine the optimal compute capacity needed. It's recommended that you start with smaller instances, scale out first, and then scale up. Also, measure the difference between CPU versus GPU needs during training and hosting. While some machine learning models require high-power GPU instances for training, inferences against the deployed model might not require the full power of a GPU. Account for inference architecture based on consumption patterns. Some models, such as e-commerce fraud detection, need to be available constantly for real-time predictions, while others, such as e-commerce forecasting models, might only need to be available periodically. In the first case, the cost of a 24/7 hosting model is justified, but significant cost savings can be realized in the second case for forecasting by deploying the model on demand, executing predictions, and then taking down the model. SageMaker Neo, Batch, and Elastic Inference can all help optimize cost depending on your consumption patterns. Define the overall return on investment and opportunity cost. Weigh the cost of adopting machine learning against the opportunity cost of not leaning on ML transformation. Specialized resources such as data scientist time or model time to market might be your most expensive and constrained resources. The most cost-effective hardware choice might not be cost-optimized if it constrains experimentation and development speed. A cross-functional team can also help determine which opportunities to pursue based on return on investment and a deeper knowledge of the efforts required. So I hope you've enjoyed this Chalk Talk on designing AI applications. Now, for more information on well-architected in the machine learning lens, be sure to check out the well-architected website. For more information on SageMaker, be sure to check out the SageMaker website. Thanks again.